Thank you, everybody, for coming. The title of the talk, I think, induces a lot of hype. Keep in mind that the second word in the title is the operative word. So this is an attempt at demystifying Bayesian deep learning. Thank you all for coming. My name is Eric. I work at Novartis. I just joined recently. I just defended from grad school, so very happy about that. Oh, thank you. So if you want to follow along, you can scan the QR code. It'll bring you to mobile-friendly HTML slides. In this time that if you haven't yet scanned it, don't worry. There is a link to the slides as well. It's also the last thing I tweeted on Twitter. And for those of you who might be looking from behind and can't, or if you come in late and if someone comes in late and they need to look at the slides, on the bottom left-hand corner of every slide, that watermark will show you the GitHub repository where the slides can be found. All right, so you can always look at that and go to the GitHub repo. Like I was mentioning, this title is very hype-ish. I recently saw this tweet, which is the hype of deep learning. You write a post, or in this case, you give a talk with Bayesian and deep learning inside there. You fill a room with people who want to look at it rather than tens of thousands of clicks. And then something happens. Point number 4 shows up. You have all this math that's going on with crazy Greek symbols, and then you all leave, right? That's what happens with a lot of the deep learning talks. My mission is to solve point 4. I want to make sure we talk about what deep learning and Bayesian deep learning is without all the Greek, without all the math. And in fact, I'm going to show you a lot of pretty pictures. Oops. Whoops. All right. So this is a talk about Bayesian stats. And so there's always the obligatory neon Bayes rule sign. Bayes rule is from the Reverend Thomas Bayes. It's a way of inferring parameters from given the underlying data. It lives as a neon sign in someone's office. That's as much about the Bayes rule that I'm going to talk about because this is the obligatory Bayes rule slide. My modest goals today are as follows. I'm going to demystify what deep learning is. How many of you have actually coded up a neural network from scratch with backpropagation and the likes? OK, so for the rest of you, this talk is for you. How many of you have coded up a Bayesian net of some sort with, say, a probabilistic programming language or likes? All right, this talk is also for, OK, so I actually do have a purpose for this talk after all. Because I gave this as a rehearsal at Boston Bayesians, and everyone raised their hand in the crowd. And so I felt like, OK, what exactly do I have to offer? So I do have something to offer today. The goal here is to explain the intuition with minimal jargon, all right? My take-home points are twofold. Firstly, deep learning is nothing more than compositions of functions on matrices and their operations, all right? If that sounds like jargon, don't worry, it'll become clear. The second thing I want you to learn is that Bayesian deep learning is basically grounded on learning probability distributions over our parameters rather than point estimates. That's it. You can go now. Yeah. All right, so how do we build towards an intuition of what deep learning is, and how do we build towards an intuition of what Bayesian deep learning is? So to do that, I'm going to start with the simplest machine learning algorithm that everybody has already touched. As long as you've done high school physics, you've touched this algorithm. It's called linear regression. How many of you were at the Tasty talk, the BuzzFeed Tasty talk? Yeah, so you know how Tasty puts those videos where you have cheese puffs 3 ways or something? So yeah, linear regression, I'm going to show it to you in 3 different forms. Then I'm going to show you logistic regression in 3 different forms. And if you follow the parallels, you will see deep nets in 3 different forms, and you will get exactly what deep learning is all about. Then I'm going to talk about what it means to go Bayesian, again, following that parallel. And finally, I'm going to show you some example code on how you can code up a neural network in a probabilistic neural network in PyMC3. OK, are you ready? All right, let's go. So linear regression, high school physics. Y is some linear function of x. In math class, it probably was taught as y equals mx plus c or ax plus b or something. That's basically what linear regression is. We've all seen this equation before. In the event where you have not just a single x, but say 2 columns of x's, or 3 columns of x's or 9 columns of x's, then you'll have an appropriately dimensioned weights vector. So in its matrix form, it looks something like that, right? So just to give you a quick guide through these visuals, it essentially is this. I have my data. It's got 4 columns. That's x. The ellipses inside these boxes indicates that there's multiple rows. It's not just a single row of stuff. I have my weights vector. It's appropriately dimensioned. It's colored because it's a parameter that we have to learn, right? It's one of the parameters that we have to learn. The bias term, right? The slope, sorry, not the slope, the intercept term. It's also a parameter that we have to learn. And when we do this linear combination of stuff, the output is a single scalar value, right? So that's linear regression that way. There's a third way to look at this. It's as a neural diagram, right? Everybody get this, right? The first part is we do the matrix or the matrix vector multiplication to get a single dimensioned output, which then we add the bias term, which is also something that we're learning. And the output here is our y. That's the final output, all right? So shown 3 ways, linear regression, right? Do we get the tasty feel over here? All right, good. So what is logistic regression? Well, logistic regression is nothing more than you take the linear function and you tack on one more functional transform on the output, right? I take the intermediate output of the linear regression transformation and then apply a squishing transformation to squash all the output values from 0 to 1, right? So this is what logistic regression is all about. And so in matrix form, it just looks like that. I do my linear regression thing and then apply a single transform across all of the elements inside the outputs, and then I get my output, right? And so as a neural diagram, that's what logistic regression is. All we've done is we've tacked on this other functional transform in orange, which is G. So logistic regression shown 3 ways is nothing more than that. OK, so then what about deep neural nets? If you look at what a deep neural net looks like in its functional form, you'll think Greek, right? Lots of symbols, lots of, oh, crap, what's going on? Well, let's break it down. Let's break it down. I have my input data, multi-dimensional, lots of dimensions. I have weights and biases that are appropriately dimensioned that I need to learn. I do a matrix-matrix operation, which is the F operation. And then I apply a nonlinearity. And then I get some intermediate output. Then I take that intermediate output, do the same thing to that thing, do another nonlinearity, and I get my final output. And so that's what deep neural nets are essentially doing. In this particular case, I'm talking about the feed-forward setting. I'm not talking about these special other algorithms, the ConvNet or the recurrent neural network. This is basically what deep learning is, right? So how many of you work with investors? OK, yeah, don't tell your investors if a new startup comes to you asking for money, ask them for, don't be, whoa, what's going on here? Is that an investor calling? I got something to sell. Was that the, oh, what's going on? Hold on. That really should not be me. OK.
Is there a phone right there? Is that a phone? No, it's not.
No, my phone's not ringing either. Is Satya listening or something? It's OK. Let's just move on. I don't care if it's Satya. In matrix form, that's what's happening, right? That's the exact same thing represented a different way. I have my data, 4 columns of x's. I have my appropriately dimensioned weights and biases and the functional transform. And when you look at it as a neural diagram, that's what this looks like, all right? So we get the weights multiplication. We have the computational graph pushing us all the way to the output. I'll note, in a majority of cases, people generally will not show this B1, or the blue and the orange lines. They'll just squish everything together. That, for the longest time, really confused me, which is why I've elected to do this super explicit, here's every single transformation that's going on thing. All right? OK, so viewed 3 ways, that's deep neural nets. So then what exactly do we mean by going Bayesian? So by going Bayesian, like I was mentioning earlier on, in vanilla neural nets or vanilla linear and logistic regression, what we're doing is we're learning a single parameter a single estimate of the parameter that says this parameter helps us best explain what the data looks like. When we talk about going Bayesian, we treat that parameter not as a single thing to be estimated, but a random variable with other parameters to be estimated, say a mean and a standard deviation or something like that. So what we're really trying to do is we're trying to learn what the probability density is over parameter space. So here's the intuition from Bayesian linear regression. In the non-Bayesian case, I have one slope that best explains the data and one intercept, or one slope and one intercept that best explain the data. When we talk about going Bayesian, essentially all we're saying is, I don't want that just that one slope. I want the family of slopes and the family of intercepts that help explain how my data came about. All right? That's the intuition behind Bayesian linear regression. So we basically go from single point estimates, as indicated by shaded squares, to probability distributions over every single estimate, every parameter inside this model. One thing that's really cool here is the moment you treat any of your parameters as random variables to be estimated, you get an expectation and you get a variance. And once you've got that expectation and variance, all that uncertainty gets propagated down to the final output as well. So in theory, I could have actually just treated one of these parameters as a random variable, if say, for example, that was the thing that I was most interested in. But in this case, it's always most informative to just treat everything as a random variable. So with Bayesian logistic regression, same thing. We basically go from this to that. And so now, here's the intuition behind Bayesian deep nets. We go from this to that. How good are we with Bayesian deep nets? Everyone can do it now, right? Like I was saying, because we have uncertainty in the parameters, all of that uncertainty just gets propagated right throughout to the end. And so that's actually the power of a probabilistic programming language. We can intuitively specify our model with random variables as our parameters, and for free get a very easy way to propagate the uncertainty through to the end. And I'm going to show you that in a bit. But in the meantime, if you want, give it a moment to load, you can take a look at this cheat sheet. It exists on the GitHub repository, so you don't have to raise your cameras right now. One thing, so it shows the parallels between the functional, the matrix, and the computational graph form of each of these three machine learning algorithms, if you want to call logistic regression and linear regression machine learning. One thing that I've done on the other side there is show what's happening with respect to these Gaussian distributions or whatever other distributions. If we take our priors, so first off, let me introduce over here. This column here is all about what makes rational or good priors for our data, for our parameters. Over here, we might say a wide, uncertain distribution is good for the priors on logistic and linear regression. But down here, you might say, well, when we're doing deep nets, we're already assuming that we've unit scaled our data. That means we've centered the data on 0 and made sure the standard deviation of the data is also 1, right? And then when we initialize our parameters, that is each of these colored boxes, we usually take a single number from the unit Gaussian and place it inside there as the initial value, which we then train and optimize towards the best performing value. So then why not just use unit Gaussians everywhere for all of those parameters? It's a fairly rational choice, and it pragmatically speaking also works. Also on the other side, on this side over here, where I'm mousing over, the final column of stuff, you'll see that what the intuition behind what's happening is we're taking our priors, which are basically just flat Gaussians or unit Gaussians, and we're shifting them around such that the parameters, such that these shifted Gaussians help us best explain the data. And it's basically analogous to shifting a point estimate around, right? Which is what we do in the non-Bayesian framework. So that's really the intuition of what's going on when we train a Bayesian neural network. OK, so let me talk a little bit about an example coded up using PyMC3. It's a probabilistic programming language, and it provides three things. Every probabilistic programming language has to provide three things. Firstly, it has to provide a family of statistical distributions that you can work with. So it should at least provide the normal, the student's t, the Cauchy distribution, the discrete distributions, and the likes. Secondly, it should do all the fancy math for lazy programmers, right? It's got all the sampling algorithms that are present inside there so that you and me, we don't have to code up our own MCMC sampler. The third thing that it should provide is a really nice API or syntax for specifying these probabilistic models. And I can't emphasize enough how important that last point on syntax is. If you were at Nicole Carlson's talk downstairs, she talked about basically wrapping PyMC3 inside a scikit-learn estimator. That's a good thing. Be like Nicole, right? You do not want to go around inventing new APIs. Likewise, this API provided by PyMC3 is a really intuitive one for specifying Bayesian models, and you'll see that in a moment. Don't be like some companies that open source a new API that just doesn't match what we know is the intuitive way to specify a probabilistic model. I'm not going to name that company. All right, so how are we going to do this? I'm going to show you an example from a multi-class classification problem. This problem is basically structured as such. There's this data set that exists inside the UCI machine learning repository. It's called the cover type data set. Basically, without showing you what the data looks like, I'm going to tell you what the task is at hand. I have 66 cartographic variables, and I want to output 1 out of 7 different forest cover types, right? So you can imagine setting up a multinomial logistic regression or the likes to solve this. But one thing that was really cool about the original author's intent behind this data set is, can we use a neural net to make these predictions? And the answer is yes, otherwise I wouldn't be speaking here. So the network architecture that I've specified, again in this very explicit format, is one where we have these weight matrices and the functional transforms without the bias terms, right? So you'll notice blue lines are not present over here. It's got, what, 2 hidden layers with 20 nodes each, and then I'm basically supposed to predict a probability distribution over 1 out of 7 classes, okay? This is what the code looks like. I'm going to zoom in a little bit. PyMC3 is written on top of Theano. The unfortunate thing is Theano has been discontinued. So the PyMC devs on the PyMC discourse forum have been talking about, OK, what's the next backend that we're going to move to? The backend is not so important for the purposes of this talk, so we can talk about this afterwards. What's more important is the API and the syntax. This is really cool. Whenever you deal with a probabilistic model in PyMC3, you're only ever touching Python objects. That is super good because it's super Pythonic. It follows Python idioms. So don't go around inventing new APIs that don't follow Python idioms, all right? So I can initialize my weights, weights 1, weights 2, weights output. You notice there were 3 weights that I need to estimate. These Python objects also behave like matrices, right? So this is another really nice thing about using the way that the PyMC devs have set up the API. In addition to that, not only do I have Python objects as my distributions, I can do math with these Python objects, such as the dot matrix dot product and the tanh transformation, right? So I can specify a single layer this way in a very, very nice and simple, with a very nice and simple syntax. So 1 layer, 2 layer, 3 layers, and finally I have the output. The output is modeled as a multinomial output. And there's a distribution for that, just like there's an app for that. And finally, all the fancy math gets done for us lazy programmers in the inference step, right? There's this thing called auto-differentiation variational inference. I'm not going to explain the underpinning mechanisms right here. We can talk about that later. But what's really cool is it'll do the shifting of Gaussians for you, right? And once it's done with that, we can sample from the posterior distributions and inspect what our model has learned. So remember I was saying it's shifting Gaussians around. Well, when we start and initialize with unit Gaussians, everything's supposed to be centered around 0 with roughly standard deviation 1. Now we've got distributions that are shifted to the negative and to the positive side. That's just the first layer of weights. The second layer of weights is like that. The third layer of weights is like that. That's a great sign that our model is learning something. I've actually done training tasks where basically my Gaussians never moved. So that was kind of sad for those projects. Thankfully for this one, you guys get to see the results of that. If we were to look at the point estimates, that is the class that has the highest probability distribution, probability mass attached to it. So it could be 0.4 for class 1 and 0.1 for the other 6 classes, summing up to 1.0. And we just take that maximum probability thing, this is what we get. Now I've ordered my 20,000 odd samples in such a way such that it's basically block diagonal, right? So the first block is class 1, the second block is class 2. Where it's yellow in the right block on the diagonal, the predictions were right. Where it's not yellow on the block diagonal, the predictions are off. And so a neural network is capable of making good predictions. But keep in mind, we're using a probabilistic programming language, which gives us more than just the point estimate, right? We can use the probabilistic estimate, right? So rather than just plotting the single highest value that's associated with it, we can actually discern what the probabilities are, plot all of the probabilities. And this is what that looks like. But even this doesn't tell us how certain or uncertain we are about the particular prediction, all right? That's where this sampling thing really comes in handy. I can take this, and I'm happy to share the code with you guys later, and figure out what the uncertainty in the prediction is and quantify it and plot that over there. So what's really cool is this. Take a look at this probabilistic estimate and look closely at class 7. It's got really high probability mass associated with it. We're pretty sure it's not class 6. We're sure it's not class 4. There's some probability mass associated with class 1. If you look at the uncertainty surrounding that, they tell a slightly different story. We're actually kind of really not so sure whether some samples are class 2 or class 1. And we're less clear about our certainty about the classification of this class of block 7. In addition to that, if you look at class 1 and 2, it looked like we're able to sort of distinguish between these two classes, but the uncertainties tell us, oh, we're actually not really clear about that, right? We shouldn't be so confident about our class predictions when it comes to differentiating class 1 and class 2, right?
What's the difference between this slide and the last slide? I didn't understand what statistic you meant.
This slide here is the probability mass associated with each class. This slide here is the uncertainty, the quantified uncertainty. I've essentially taken the standard deviation of the posterior samples, all right? So that was basically a worked example, and I hope it's thrown your world upside down slightly. The point being here is that the uncertainty can really matter. Now, there are some places where the uncertainty shouldn't matter, right? The uncertainty shouldn't matter in these real-time applications that are streaming in milliseconds at a time. They should matter for life and death decisions, like drug manufacturing. I'm part of a drug company now, so this sort of stuff is really important for us, right? So that should be an example of, okay, the uncertainty can tell us a slightly different or more nuanced story than we were thinking of at the beginning. All right, let's loop back. This is the first take-home point. Deep learning is nothing more than compositions of functions on matrices. And this is the second take-home point, which is that Bayesian deep learning is nothing more than learning a probability distribution on each of those parameters. And I've shown you how that happens with PyMC3 code. If you're interested in reading more, take a look at the PyMC3 docs. Listen to Nicole's talk. She's got a really good talk on how do you make your PyMC3 models reusable. So go listen to her talk online if you didn't. This example exists in the Bayesian analysis recipes repository. You can click on it on the link inside the slides as well and check it out for yourself. I want to thank some people who've taught me stuff in ways direct and indirect. So their names are up there. And I want to recommend a few people to talk to, or in the case of David McKay, because he's passed away, go look up the resources that he's left behind for us. They're a valuable, valuable, wonderful resource for us to learn stuff from. All right, with that, I want to say thank you for your time. Happy to take questions.
Have you looked at any ways about using this uncertainty to improve your models, making a mini batch of just examples where
Definitely. So one way that we can take this further is to actually, so the question was, have I looked at ways of harnessing the uncertainty to train a better model, essentially. And so one way that you can imagine doing this is by taking the data from class 1 and class 2 and training a separate classifier for that particular case, right? And because this evidence here would bear out, oh, OK, when training across all 7 classes, we're not really able to do so. Maybe we can find either a different training scheme or find more data to help us distinguish between those 2 classes. Or it could also be like, this is cartography. I'm from biomed, so I don't really know geography very well, but potentially cartographic variables are not good enough to discriminate between 2 really similar forest cover types, or 2 cover types that are distinct but happen to show up on the same cartographic regions. On the left, and then at the back, and then Chai at the back.
How much more expensive is this than just training standard and neural network?
20 times more expensive.
No.
Yeah, no. So if you can, plus minus 3. No, I'm just joking. If you were to train the same neural network architecture in Keras, it'd be slightly different because it has the bias terms built in, but it trains really fast. This thing took about 40-odd minutes to train on 20,000 data points. My guesstimate on how fast it would take with Keras is something on the order of like 10 minutes to 5 minutes to finish training. Now, that said, I wasn't taking advantage of what we call mini-batch ADVI, which allows us to train really fast, and that's actually one way to speed up training of Bayesian models. For the record, like how to train Bayesian models, Bayesian deep neural networks really efficiently is a super active area of research right now. So lots of uncertainty. Boom. Lots of uncertainty in the field surrounding that right now. So lots to learn as well.
And how would you compare the performance of the models? I don't know.
Yes. If you look at the Bayesian analysis recipes repository, you'll find the multinomial logistic regression and the Bayesian neural net as separate notebooks. And you'll see that the Bayesian neural net gets AUROC on the means at roughly 0.80-ish, and AUROC with multinomial logistic of 0.72. So considerable performance going to a deep net, right? Then of course, the advantage of going Bayesian is we get the uncertainty. I had the 2 questions at the back.
The timing was my question. So.
Oh, OK, all right. Oh, so how does Bayesian inference work when we go to higher dimensions? So you're essentially saying, what happens when we increase the number of hidden nodes? Same exact thing. You don't have, but it trains slower because we have more parameters to fit. Convergence. Now that's something I've not tried. Granted, though, the number of data points is 20-something thousand. What's this? 70 by 20 is 1,400 plus another 400, 800. So we're still under parameterized with this model. We don't have more parameters than data points yet. So yeah, there's room to grow. There's room to grow. One back here and then one in the front.
So you looked at the distributions around your individual parameters. Is there anything to be gained here for the correlation between the different parameters?
Correlation between the parameters. And I've been asked that question, and I've been asked that question in public talk settings, and I've asked that question to myself on my own. And truth be told, whenever you look at a deep net, and you try to ask, what's the meaning of this? What's the interpretation of the weights matrix? That's essentially the heart of the question, right?
Well, yeah. So in physical systems, like when we fit physical models,
yeah.
Sometimes if we've overcomplicated a model and really strong correlation, complicated model.
Right.
I was wondering if something happens like this where you don't have a physical intuition necessarily, but you might have parameters that are perfectly correlated.
It's witchcraft to determine how many parameters inside there. So the number of parameters is essentially determined by conceptually how many nodes we want inside there. And so I might be uninformed about this, but my best guess right now is that there are, apart from trial and error or Bayesian hyperparameter search, there's no good way of determining how many parameters we need inside there. There's no principled way. There are good ways. Just flood Amazon, right? And you'll get your answer.
So thanks so much. This is so between you and Thomas Wickwicki, I've seen some reasonable examples of when to use Bayesian things for classification. I've yet to find a good example or a good reason to use it for regression or regression style problems or unsupervised learning. Can you think of a defense for this, or would you claim that it's probably best to stay within the classification context?
When uncertainty in regression estimates can be tied to company bottom lines, then we've got a good reason to do that. For unsupervised, I truthfully don't know. I really don't know. That's something I'd have to read up, and maybe we can chat about that later.
Sure, great.
Back there and then up front.
When did you drop bias terms?
Fewer parameters, laziness. No, I'm just joking. I've trained it with the bias terms. It trains, for some reason, significantly much slower with the bias terms. And I don't mean that it just trained with the, so I'm not saying that it added a linear amount of time to the training time. I'm saying it really trained much slower. And I couldn't figure out why. So I dropped the bias terms. In any case, we're under-parameterizing the problem anyways. So we're sort of forcing the neural network to learn and compress data, which is sort of the intuition behind why neural networks do so well. So yeah, it worked out fine. So there was no principled reason for that.
I was just wondering if you could comment about traditional neural networks. You need a cajillion samples of data to be effective. Does using priors intelligently help compensate for that in the case where you have less data?
Yeah, definitely. Oh, and something I actually learned last week reading Radford Neal's book. Radford Neal is basically the father of Bayesian neural nets, so that was his seminal thesis work. You don't need to do train test splits when you go Bayesian. That was mind-blowing. Go read Radford Neal's book if you can get access to it. If you can't, you do not need to split your data into training and testing sets. Whatever you fit, the posterior distributions. This is super controversial, I know. I'm facing a crowd that's like, what? You do not need to do that according to his book. And I have a small blog post on my website quoting the relevant sections of that book. It's really neat. I was mind blown. And I also was like, what? OK, question there.
So you don't have to take Bayesian estimates for your distribution parameters, right? You could actually take point estimates for your distribution parameters, and that would speed up the training. Why wouldn't you do something like that instead of actually?
So you're saying basically rather than fit the full distribution, fit just the mu and the SD, right? Yeah, I think that's OK. I can't speak intelligently to whether that's happening behind the scenes, but yes, I do know that when you train a Bayesian neural net, you double versus like point parameters, you do double the number of parameters. So it should be that when we're using Gaussians or two-parameter distributions as priors on our parameters. Wow, so many parameters. You basically double the number of parameters that you need to learn. One more question.
If you start iterating around your model and you choose different distributions for the priors and for the data, how does that affect the accuracy of your fits? And then a follow-up to that is, how well would the variational base approximation work if you start changing the distribution versus a proper sampling?
OK, so first question is, what would happen if you changed the likelihood function for the data? What would happen if you changed the priors for the parameters? If you get the likelihood function wrong, you'll be doing something that I blogged about recently, which is fitting Poisson distributions to data that had negative values inside there. Wrong. Poissons are all positive. You do not get. So make sure you cannot get the likelihood function wrong. You always have to get the likelihood function correct. On the other hand, if you change the priors for the parameters, what you're basically expressing is, I know a little bit more than my flat priors, or I know a little bit less than my flat priors about what this parameter should be. And so you should have a justified reason for changing the priors on that. So when we talk about going Bayesian, essentially, we're, like Andrew Gelman was saying, getting rid of p-values, those detestable things, right? So we're getting rid of p-values, and we're making science more a more discourse type of thing. I come to you with my priors, and I justify them. I give you good, strong reasons that aren't grounded necessarily only in math that say why these priors are good, right? It may be an empirical Bayes thing. I cheated and I did the frequentist thing first, and then I use those as the priors, right? It could be something like that, or it could be I have absolutely no reason to believe anything, and so I put a completely uninformative prior, and I'm bringing this to you, the model critiquer, to say that's what I believe. That's what I believe, and I can give you reasons for why I believe we should not know anything about that. That's the nice thing about going Bayesian, right? We don't have like cutoffs and things to help us shortcut science. We actually bring back science to this dialogue thing where we're saying, I need to argue forcefully with reason about why my model is the right model, why my priors are the right priors. It's tougher work, but it's better work. Did I get, yeah, okay, cool. Sorry, philosophy of science permeates this frequentist Bayesian thing as well. So thank you very much. See you at the networking.